Hello, welcome back. In this segment, I'm going to talk about Schnorr zero knowledge proof for Diffie-Hellman kind of setup, meaning we are going to make use of the discrete logarithm problem and use that problem as an underlying hard problem for identification purposes. Okay, that's the bigger picture. Okay, there are multiple segments into this topic. I will pick up only one. In particular, I will talk about Schnorr interactive version. There is a non-interactive version as well, but I will first start with the interactive version. Okay, interactive means the two parties will exchange messages. One party will try to convince the other party, and the other party will verify. Okay, that's basically the interactive. I will talk about the details. Okay, in a moment. In this context, zero knowledge means that remember I was talking about a discrete logarithm problem earlier. And what is zero knowledge in this context? In this context, zero knowledge means like this. Suppose you have a random number R. Okay, you compute G power R in some cyclic group. G is a generator of a cyclic group. You get some result. Let's say you get some result capital R for a moment. Okay. We know this is a hard problem, meaning given R, given the capital R and G, finding the small r is not known to be easy in general. Okay. So the idea of this zero knowledge proof in this context means that you wanted to show to other verifier that you do know the small value of r, but you don't want to share that small r value with anybody else. Okay. It's like you have some secret and you wanted to tell to others that you know the secret, but you don't want to share the secret. That's like a kind of a magic. Okay, that's what they mean by zero knowledge. Okay. All right. So let's get straight into the problem we are going to talk about today. The problem we are going to talk about today is the identification part. Okay, there are two parties, Alice and Bob. Alice wants to convince Bob that Alice knows the private discrete logarithm or the private exponent. Okay. And Bob will verify that Alice indeed knows the private exponent. Okay, that's basically the bigger picture. Okay, as I mentioned earlier, this article has multiple segments, and I'm going to only talk about interactive version of Schnorr identification scheme. Furthermore, the article also talks about two different setup. One is the finite field, another is elliptic curve, and I'm only going to talk about finite field in this segment. Okay, all right. I'm going to make use of all the variables they have defined here. So we have two parties, Alice and Bob, right? I will draw Alice here and Bob here. Okay, Alice is here. Bob will be the verifier who wants to verify that Alice indeed knows the private exponent. Okay, I'll formalize all of this in a moment, but let me get the basic idea across first. Here is verifier who's going to verify the correctness, and here is the prover. Okay, who's going to prove to Bob that he knows the secret. Okay, prover. So in order to run this protocol, we need to make sure that both Alice and Bob already agreed upon some public parameters. Okay, so what are the public parameters in this context? So the cyclic group G, capital G, it can be any cyclic group. Okay, but the group is going to be something like this. Suppose your P is say 2Q plus 1, and P and Q are prime numbers. Remember, this group we played with earlier when we talked about Diffie-Hellman, we can select the group to be this the group generated by a generator of order Q. Okay, that's the group that I'm going to work with. Okay, the details will be clear in a moment. So you have a group. Don't worry what the group is at this point. Some group and a generator of a group, and the order of the group is Q. Okay. What else they need to agree on? That's basically the basic parameters they need to agree on. Both of them know these parameters. Okay, and before this protocol starts, Alice has to generate a private exponent A, small a, okay, which she's keeping it for a long time. She may have to do a key rotation now and then, like a certificate kind of thing. But her private key is small a, okay, only she knows. So I will go and put it inside her box. This is her world, if you will. Okay. So what she's going to do, she's going to publish G power A. So I have to assume G power A. Let's call G power A to be capital A. Okay. Capital A means G power A. So I'll write it here. Capital A is G power A. Okay. So these are the public parameters. They both know. Of course, small a is only known to Alice. Okay. G power A is computed in this group G. Okay. All right. And now let's start the protocol. What is the first thing Alice will do? Well, the goal of Alice is to basically convince Bob that she knows the small a. Okay, small a is the secret, remember? But she of course will not send a to Bob. Then Bob will know the a. Okay. So how can she convince now that she knows the small a? The first step in this protocol, excuse me, is let Alice generate a private variable value. Let me use small v, okay, which is a value from the group Z Q. Okay, remember Q I assumed as a prime number, so ZQ means all numbers from 0 through Q minus 1. Okay, protocol, Alice first generates a private variable v, small v, which is an element from 0 through Q minus 1. Okay, and she generates a capital V, which is nothing but G power V, and she sends capital V to Bob. Okay, so Bob gets capital V. Remember, Bob cannot compute small v from capital V because that's a discrete logarithm problem. So Alice sends capital V to Bob. So what will Bob do? Bob will take, Bob will actually generate another random number C. Okay, C is, you can imagine, as a challenge. C is a number belonging to the group ZQ, meaning a number between 0 through Q minus 1, or it can be only 2 power T minus 1. Okay, so it can be either an element of ZQ, or if you don't want very, very large C, you can also limit to something reasonable. T can be, for example, 160-bit. That means C is an element belonging to the interval 0 to 2 power 160 minus 1, which is an enormous number. Okay, and you can increase that value of T as you desire. All right, so this is basically sent by Bob back to Alice. And what will Alice do with that C? She's going to compute a small r, which is nothing but v, small v, only she knows the small v, okay, minus her own private key, small a, and the C that she received from Bob. Okay. Okay, here is a little bit of caveat. This is computed with respect to the group ZQ, meaning mod Q. Okay, this is important. And it's going to be clear why it's not mod P, it's why it's mod Q. It's important. Okay, I'll be explaining that in a moment. Okay, this is the value of R she computes, and she sends that R to Bob. Okay, what will Bob do with R? Bob takes the R and is going to compute G power R. He multiplies it with capital A, which is publicly known, with his small c that he picked, and he's going to check whether this is equal to, is it equal to the capital V. Okay, why is this enough? Okay, let me now prove to you what is the meaning of this expression. So this is basically it. Bob was able to convince himself that Alice knows the private value small a. Okay, without Alice revealing the small a's. Okay, that's the idea. All right. So the obvious question is, why is this correct? Okay, why can't an attacker cheat the system and prove that he knows the small a as well. Okay. Let me explain one more thing. Alice publishes her public key capital A, right? That capital A must be verifiable by anybody, meaning they should be able to associate capital A with Alice. Saying, all right. So remember, only thing Bob verifies is that any request that comes in who claims that they know the small a, he can verify it. Okay. Alice is not actually verifying whether she's talking to the right Bob. That's not part of this discussion either. Okay, but those are some small low-level details. At this point, I just want to get across the important message that there's a way to verify whether Alice knows the small a. Bob can verify that. Okay, this is a hard problem in cryptography, right? As far as we know, number theory problem. Given a group G and given an element small g power a, where G is the generator of the group, right? Given capital A, we don't know how to find a small a. That's the discrete logarithm problem. Okay. All right. So this is basically the theory part. Now let me show to you why is this secure. First of all, okay. First of all, think about this way. Capital A is a random number because small a is a random number. So G power A is going to be a random number. There's no structure about a small a revealed in capital A as far as we know. So capital A is a random number. That's the assumption. Okay. What about small v? Small v is also a random number because Alice is picking randomly from the group ZQ. Okay. What about small c? Small c is also a random number. Okay. So now let's get into this R. R is small v, which is a random number. C is a random number. A is also a random number. Okay, so R itself is a random number. Okay, it's somewhat very similar to affine cipher. Actually, in affine cipher we have something very similar. Instead of minus, you put a plus. That's all. That's the only difference. Okay, so this number R is actually a random number. So somebody eavesdropping this connection between Alice and Bob, they actually don't get much by eavesdropping because V is a random number, C is a random number, R is a random number. Okay, and R is an independent random number because it's made of two random numbers and a mod Q. So it's like an affine cipher basically. Okay, one time we're only using it one time. That's another important thing here. V is unique per session. V is generated whenever a session is established. Similarly, C is generated whenever a session is established. As a matter of fact, you can easily find a small a if V is repeated because you just have to subtract two of the R's and then you'll easily be able to do that. Anyway, I'm not going to talk about that now, but let me focus now on the fact that R is a random number. Therefore, if an attacker wants to break this, he can actually directly set up a session with Bob. Okay, let's assume attacker was able to break it for a moment, meaning he was able to guess an R in such a way that he got this answer successful, meaning he tricked Bob to get a correct verifier value V, because the V is the value that Bob picked, capital V. Okay, let's assume he was able to do that. That means we can also assume that he was able to do it for two different R's. Okay, if he was able to do it one R, then he should be able to do it for two different R's, right? Okay, so let's continue the proof now. Okay, the proof is as follows. Let us assume he was able to successfully trick verifier Bob to accept the fact that V is equal to capital V, right? Capital V is equal to G power small r times capital A. Attacker was able to convince Bob that he knows R. Okay, that means he should be able to convince two times. If he's able to convince once, he should be able to convince two times. So let's assume he fixes the small v. Oh, he doesn't know the small v, he knows the capital V. Okay, so what we are going to argue is that if he is able to convince once, so he should be able to convince multiple times. That means he should be able to come up with two different R's such that V is capital V is equal to G power R1. Okay, for capital A power C1, because whenever you interact with Bob, you get a new C, so he's going to give you C1. And we say he was able to also reuse the same V, same capital V, and come up with another R2, right? Because he can fix the same V, okay? And since he has this magic where he can derive an R to satisfy, so you should be able to derive multiple R's, okay? Times A power C2, because he's going to interact 2 times with the verifier Bob. Okay, now if you reorganize this little bit, you know, apply the power rule and so on, you should be able to come to the conclusion that R1 minus inverse is nothing but small a. This is amazing, in mod q. Okay, this is in mod q because remember, exponents are always in mod q. Okay, that's something, a property that we talked about earlier. Okay, I'll recall it quickly. Suppose you want to find the value of g power x. Okay, x can be any value in mod p. Okay, it's enough to do what is the order of the element g? G generates the entire group of order q, right? That's the definition. That means instead of computing g power x, we can compute g power x mod q. Which means the attacker was able to compute the small a. Okay, that means he was able to solve the discrete logarithm problem. Given capital A, the argument was that there's no easy way to find a small a. That is what we assumed, the world assumes, that he broke the system, okay, which is bad. Okay, that means there's a contradiction that he was able to guess the value of R in such a way that he will pass the verification. Okay, that's not possible. Okay, so now some details about the group, how I implemented it. I generated a safe prime P such a way that P is equal to 2Q plus 1. Okay, and I also generated a generator G for this group. Okay, G generates a cyclic group of order Q. Okay, that's basically what I did. So what group am I working with? The group G is nothing but the group generated by this element G of order Q. Q is a prime number. Okay, that's the implementation detail. But the demo, I'm going to make use of NIST data. So NIST has already provided group G generator and the order of the group Q, and I will show to you now how this verification is working. Okay, and now we are calling the main function with that PQG from the NIST data, and let's now run the protocol, and I will walk you through the output. Okay, there's a lot of numbers here, so I need to show to you step by step what's happening. And the first step is that the prover Alice generates a long-term private key. Okay, she generates only once, and she is using it for quite some time. And she publishes her capital A to the world. Okay, and now let's run this protocol. Okay, what is the first step? The first step of the protocol is that the prover publishes after the prover Alice publishes her public key. A prover generates an ephemeral key. Okay, ephemeral key means something that changes, the small v. She generates that, but she doesn't publish that, of course. And then she publishes a public key associated with the private key, the ephemeral private key. And the challenger generates the challenge C, which we talked about on the whiteboard, a T-bit number. T, I assume to be 160. You can increase it if you want. That's not a problem. And then the prover generates this random number R based on a V, A, and C we talked about on the whiteboard. And then the verifier checks whether G power R times A power C is same as the capital V. Okay, in that case, what happens now at the end? As you can see, the verification successful because the verifier was able to convince. Okay, now let's pretend that I am a bad guy and I don't know the small a. Okay, so what if I just send some random number, secrets dot random bits, okay, of T. Okay, some random bits. The verification should fail now, right? Because I don't know. You see here, verification failed. So signature verification is kind of, it's not exactly a digital signature at this point. It's an identification scheme, but you are trying to prove that you know small a. Okay. So anyway, only if you know small a, and that we assume the the discrete logarithm problem is hard, then the scheme works. Okay. That's all. Thank you very much.